like to welcome everyone to our second meeting of our remote continuation of the celebration of the 80th anniversary of Professor Jaco Palish. Well, before we start, I would like to kindly ask everyone to maintain the microphone off and only activate it when asking a question to reduce the chance for interference. So it's my great pleasure to introduce our speaker today, Pedro Duarte from University of Lisbon. He will speak about the Hölder continuity of the Lyapunov exponents for linear cocycles over hyperbolic dynamical systems. Please, Pedro.
Okay, thank you very much, Silvius. This is, let me read just a brief note. This was a talk that I was supposed to give during Jaco's 80th birthday. Fortunately, I could not go. And so this is just a brief note. So the keyword Lyapunov exponent in the title brings me back to my PhD time at INPA under the supervision of Jaco Palish, when among other things, I have learned and started to work on the standard map, a model which is famous for the hard and open conjecture about the positivity of its Lyapunov exponents. These results, although not about the standard map, were certainly influenced by my previous experience while working on this model. I want to express my depths of gratitude to Jaco for the support and confidence that he always placed in my work during all these years. So thank you very much, Jaco. Now, my work is a joint work with Silvius Klein and Mauricio Paletti. And let me start with some terminology. So the plan of my talk is to give you the statements, then to go through a quick revision of results, related results on the same area that were known before. And then the rest of the talk, I will try to give you an outline, the strategies basically for the proof without any kind of technical details. So all details will be hidden in this presentation, all technical details, I mean. So linear cocycles, I guess everybody knows what's a linear cocycle. It's a bundle map over some base dynamics, which I will always assume to be a measure-preserving, ergodic measure-preserving transformation. And then this bundle map is a fiber action, which is ruled by a bounded and measurable function with values on groups, say the GLD group. Usually, we refer to this function as a cocycle also. Then the iterates of the cocycle are given by this kind of expression, and we are interested in Lyapunov exponents. So this is the first Lyapunov exponent, or the top Lyapunov exponent. And these terms here under the limit, I will refer to them as finite scale Lyapunov exponents. So it's the Lyapunov exponent at time scale n. And the kind of problem I want to address is the problem of continuity of the first Lyapunov exponent on a suitable space of cocycles, regarding the cocycles as measurable and bounded functions in a group, in a GLD group, and the base dynamics is fixed. So I forgot to say in the beginning, but please interrupt me at any time if something is not clear. Okay, so the result is the following. We assume some sort of hyperbolicity on the base dynamics. So we model the base dynamics by Bernoulli shift in finitely many symbols, and we choose a measure, not necessarily a Bernoulli measure, but a measure which is hyperbolic and mixing with a local product structure with Euler density. And then we consider a space of cocycles, the space of Euler continuous fiber-bunched cocycles. Okay, this is a technical assumption that I will give the definition in a minute. And then with this definition, and the distance that we are going to consider is the uniform distance between cocycles. Okay, and then the result says that in this space of fiber-bunched cocycles with this uniform distance, if we take cocycles which by a generic condition, so-called pinching and twisting condition that I will also give you the definition. Although the definition will not be relevant for what will follow, because this will be part of the technical details that I will hide. So the important thing is that these conditions are generic. And then if you take a cocycle, there is a neighborhood of this cocycle where all the Lyapunov exponents are Euler continuous. So we only need to deal with the first Lyapunov exponent because there are standard techniques, multilinear algebra techniques that allow us to reduce the problem of the continuity of other Lyapunov exponents to that of the first. So from now on, I will basically focus on the first Lyapunov exponent. And so fiber bunch means that you have an hyperbolic base dynamics, and it means that the bundle map is partially hyperbolic. It's partially hyperbolic where the center direction is the fiber of the cocycle. So it basically means that the hyperbolicity on the base dominates the fiber on the linear action of the fiber bundle. So this definition appeared in a paper by Christian Bonatti, Xavier Gomez-Montt, and Marcel Viana. It's a paper about it's a paper where they prove that generically the Lyapunov exponents are positive for linear cocycles over hyperbolic dynamics. In this paper, they extend the previous old result from the 60s by Furstenberg, where he proved the same kind of thing, but for linear cocycles over Bernoulli shifts, okay, for the so-called random linear cocycles. And so there are many things that I could say about these fiber bunch cocycles, like that they always admit holonomies that allow us to identify fibers along stable and along unstable, strong stable and strong unstable manifolds. But I don't have time to go into these details. Then the second definition I wanted to give you is this definition of pinching and twisting. The definition that you can read here, I took it from the paper of Arthur Ávila and Marcel Viana, the paper called Simplicity of the Lyapunov Spectra, Sufficient Criteria. This is a 2007 paper where they extend another result by Roggi and by Wivac and Roggi, where they extend the previous result of Furstenberg. They give a criteria for simplicity, this for random linear cocycles, that is linear cocycles over Bernoulli shifts. And in this paper, they greatly extend this result for very general hyperbolic base dynamics for linear cocycles over very general. And of course, they need to make this kind of assumption that the cocycles is fiber bunched. And then these are the conditions that are these are the generic conditions that allow to get this kind of simplicity. So these conditions imply that the spectrum is simple in particular. So all the Lyapunov exponents are different. Sorry for not reading this, but I will not really use the content in this definition. Okay, then before I pass to the historical review of what was known before, let me just set the definition of what is a random linear cocycle. So you fix a measure. For simplicity, I assume this measure is compactly supported. So it's a measure on the group GLD. And then we consider a Bernoulli shift on the space of sequences of matrices. And we endow this space of sequences with a Bernoulli probability, mu to the power z. Okay, and then the function that gives us the fiber action is just this locally constant function that depends only on the zero entry. So it's a function that takes a sequence of matrices and reads the matrix at the zero position. Okay, the shifts, the iterates of the Bernoulli shift, when we look this observable under the iterates of the Bernoulli shift, we get an IID process with common distribution mu. Okay, so this is the usual setting when we talk about random products of matrices in the IID sense. Okay, and then the linear cocycle is this map. Okay, it's the usual definition. And the problem here is the continuity of the first Lyapunov exponent, say, as a function of the probability measure. So in this space of probability measures, we can put the weak star topology. It's a natural topology, but this topology is not enough. So one needs also that the supports of the measures to be close to each other. So we should add an Hausdorff distance between the supports of the measures. And actually, some of the results that I'm going to tell you about, they prove continuity with respect to a slightly stronger topology, which is a topology determined by the so-called Wasserstein metric. Okay, but I don't have time to go into what is it. So now I'll give you a list of results that were proven along the years in this same direction. So first list of results will be about a random case. So locally constant linear cocycles over Bernoulli shifts. The oldest result is a result of Furstenberg and Kiefer, 83, where they prove continuity under generic irreducibility assumptions. Okay, the main idea to prove this is a formula which was established by Furstenberg in the 60s. It's a formula that gives the first Lyapunov exponent. It's an integral formula that gives the first Lyapunov exponent in terms of the so-called stationary measures. And because in general there are several stationary measures, for the formula to be correct, one needs to take measures that maximize something, some quantity. But generically, there is a unique stationary measure. And whenever there is a unique stationary measure, the formula of Furstenberg gives easily the continuity. So this is a very, very rough idea. The idea to prove Furstenberg theory is really simple. Is basically the Furstenberg's formula. Then in 1889, Emile Lepage generalized this result with the same sort of hypothesis. He proved Euler continuity of the Lyapunov exponent. And this is the result we are now generalizing, because instead of a Bernoulli shift on the basis and a locally constant cocycle, we are taking an Euler continuous cocycle, fiber bunched, over a more general hyperbolic base dynamics. Okay, and the strategy to prove Emile Lepage is spectral. So he uses spectral theory. There was a theory, spectral theory that was developed to prove statistical limit theorems like central limit theorem, large deviation principles, and so on for Markov processes. And the strategy of Lepage was to use this theory to prove the continuity. Okay, and then later in 2007, there was a paper of Marcel Viana and Carlos Bocar Neto, which was only published a few years later, where they prove continuity without any generic assumptions, but for GL2, for 2x2 cocycles. Okay, so this is again locally constant cocycles, so it's the random case. And the extension of this result to higher dimensions was announced some years ago with a result by Arthur Avila, Alexander Eskin, and Marcel Viana, and it's the exact same result, but for higher dimensional cocycles or matrices. This result, as far as I know, is still we are still waiting for it. But anyway, it's there is the okay. Now let me say a few words about what is known when the base dynamics is a bit more general. It's an hyperbolic dynamics. First of all, in the previous paper of Viana and Bocar Neto, they gave a counterexample to continuity. So they considered a random cocycle, so a locally constant cocycle over Bernoulli shift, but now they looked at the space of older continuous cocycles, so a larger space of cocycles, and they proved that they have an example where the Lyapunov exponent becomes discontinuous in this larger space of cocycles. Okay, and what happened in this broader space of cocycles is that the discontinuity is obtained via cocycles which fail to be fiber bunched. And so later in his book, Lecture Notes on Lyapunov Exponents, Marcelo formulated a conjecture that equated fiber bunched with the continuity of Lyapunov exponents. So he conjectured that these two statements were equivalent. And One of the implications of this equivalence was proven a few years ago by Lucas Bacchus, Aaron Brown, and Clark Butler. So in the GL2 case, if the cocycle is fiber-benched, so all the continuous and fiber-benched cocycles, the Lyapunov exponents are continuous. This is true without any kind of generic hypothesis, so this is true always. So for higher dimensional cocycles, of course, this is completely open. So this result gives continuity of the Lyapunov exponents without a modulus of continuity in our setting. But in general, for, say, higher dimensional cocycles, I'm not aware, maybe there are, but I'm not aware of results proving, say, continuity with some sort of generic assumptions of the Lyapunov exponents of linear cocycles over an hyperbolic base dynamics and this class of linear cocycles fiber-benched. So I'm not aware, maybe there are. Anyway, our result, what we want to do is to go beyond continuity in a qualitative sense. We want to prove, to get Euler continuity, and Euler continuity, by the way, is the strongest form of continuity that we can hope for, at least if we stay aside from the uniformly hyperbolic case. For uniformly hyperbolic cocycles, you can get better continuity. The continuity can be as good as you want, but in general, there are counterexamples that show that you cannot go beyond Euler continuity. Okay, so now let me pass to the strategy of the proof. There will be several reduction steps. In the first step, we use a result that me and Silvius proved a few years ago and called it the abstract continuity theorem. So it's a theorem for the continuity of the Lyapunov exponents. So if you have an ergodic measure preserving transformation and you fix a space of cocycles endowed with this uniform distance, so it doesn't really matter what the space of cocycles is, then there are several technical assumptions. I'm making the result simpler than what it is really. But the idea is that if you have a cocycle which has a gap between the first and second Lyapunov exponent, and if this cocycle satisfies fiber uniform large deviation estimates of exponential type, I will show you what this means in the next slide. So if this is the big assumption of the theorem, then we have Euler continuity of the top Lyapunov exponent. Local Euler continuity, I mean, there is a neighborhood of the cocycle where the first Lyapunov exponent is Euler continuous. So now, what is fiber large deviation estimates? If you think of a linear cocycle, then when you look at the finite scale Lyapunov exponents, they converge to the asymptotic limit, which is the Lyapunov exponent. This is by Furstenberg and Kessen. And so because almost sure convergence implies convergence in probability, the probability of this tail event tends to 0. So for every delta that you consider, this probability must tend to 0. And what we are saying is that this converges to 0 in an exponential way. It is a geometric convergence. And moreover, this convergence is uniform in a neighborhood of A. So the definition is that given A, there is a neighborhood of A such that for any delta, there is a constant which depends on delta in this way. It's bounded from below by the power of delta, such that for all cocycles in this neighborhood, you get this kind of result. So it's a form of quantitative, or it's a speed of convergence for convergence in probability of the finite scale Lyapunov exponents to the limit quantity. Okay, we call it fiber by the obvious reason that this involves the fiber action of the cocycle. We can define the exact same concept associated with the Birkhoff theorem. Say, whenever you have an observable psi or phi, by Birkhoff theorem, if the base dynamics is ergodic, you know that these Birkhoff averages converge to the space average of the function. And this convergence is almost surely. This implies convergence in probability. So the measure of this tail event or rare event tends to 0 as n tends to infinity. And we are assuming uniform and geometric convergence and exponential convergence to 0. And we talk about base uniform large deviations of exponential type if this holds uniformly in a neighborhood of the observable phi. Okay, and if there is a whole space, normed space of bounded cocycles, such that this is true for all cocycles, and these constants here depend only on the norm of the original cocycle, and they are uniform in the neighborhood, then we say that the space H satisfies base uniform large deviation estimates of exponential type. And again, this is a quantitative form of expressing this convergence in probability. Okay, then how to prove large deviations? There is a result relatively recent that it's a very nice result that establishes large deviation estimates for the space of Lipschitz observables. So Jean-René Chazot and Sébastien Guezel in 2012, they assumed that the base dynamics is hyperbolic. In this sense, it's modeled by a Young-Tower exponential tails. And then they proved that the space of Lipschitz observables satisfy uniform large deviations of exponential type. Actually, they proved a bit more. They formulate what is a concentration inequality for dynamical systems, which is something stronger than these uniform large deviations. But I will not give you the definition of this. This is a very nice result that establishes this kind of estimates that we need in the setting of dynamical systems. Now, next step, next reduction that I want to tell you is how to reduce fiber to base large deviations. So there are these two types, parallel types of large deviations. One is for cocycles, and the other is for observables, real valued observables over an ergodic dynamical system. And there is a standard way of doing the reduction of fiber to base large deviations. And it's done in this way. So you look at the cocycle and you look at the action of the cocycle on the projective space. Say where you had the action on the Euclidean space, you now consider the projective space, and you look at the projective action of the matrices of the cocycle. So this is the action induced by the linear cocycle. It's the projectivization of the linear cocycle, if you want. And then think of this observable. This observable here reads a point and a vector and basically estimates the norm expansion of the matrix along this vector. The logarithm is just to bring this to an additive language, okay? But I will keep the language of norm expansion, simply ignoring the logarithm. And then if you iterate n times your vector and you want to estimate the norm expansion of this vector along n iterates, this, because I'm taking the logarithm, this norm expansion can be split into individual norm expansions at each iterate. And then you have this equation that this norm expansion can be expressed as a Birkhoff sum of this observable above. And then if we divide by 1 over n, we get that the finite scale Lyapunov exponent on the left equals the Birkhoff average on the right. Okay, and once you have this kind of equation, it's easy to see that if we can prove base large deviations for the above observable, so if for this observable we can establish base large deviations, and these large deviations hold for a class of observables that include the above observable, then from this it's not difficult to get fiber large deviation estimates. So this is a strategy to reduce base to fiber to base large deviations. There is a problem though. We would like to be able to apply René Chazot and Sébastien Guezel result, but we cannot. The reason why we cannot is that even if we assume that X is a nice, the action on the base is a nice hyperbolic dynamical system, when we add the projective action, we lose this uniform hyperbolicity. In general, we cannot hope that this map is has the kind of uniform hyperbolicity that would allow us to apply the previous result. So we cannot use this result. We have to redo everything from scratch. And the strategy to redo it is to use the same kind of approach that Émile Lepage uses in his random case, in the random case. And so the approach is probabilistic. So the next slides, I will show you some concepts that appear in this theory of limit theorems, like central limit theorems, large deviations, and so on for Markov processes. So a key concept is this that I'm calling stochastic dynamical system. A stochastic dynamical system for me is a continuous map that to each state in some compact metric space associates a transition probability. So different names for this object could be a transition kernel, because it gives me the transition probability of going from one state to the next state. Another name could be Feller kernel, because William Feller studied Markov processes that preserve the kind of continuity that corresponds to asking to assume this kind of continuity. Okay, so, but I will call them stochastic dynamical systems or kernels or whatever. So in this probabilistic language, when you have a state, you can think of the orbit of a state, initial state X, as a random walk. It's a random walk on the space sigma. And the idea is that this random process, this random walk starts with X, and then the above kernel gives me the transition probabilities from one moment to the next, the transition probabilities on the state from one moment to the next state. And we want to translate this to spaces of sequences, because it's nice to be able to express these more probabilistic statements in a more dynamical sense, say using shifts, Markov shifts. And for that, it's a classical construction that for any probability that you take on the space of states, so you can think of this as the initial distribution of your random walk, then there is a unit probability on the space of sequences such that this canonical random process, it's the process that reads the states at every position, and this random process becomes a random walk or a Markov process with initial distribution theta and transition probability kernel k. Okay, and so this allows us to bring this to a more dynamical language. First, we say that the measure theta is stationary if the random walk that is associated with it is a stationary random walk. And this can be formulated in either of these ways, okay? And then it's not difficult to see that this measure is shift invariant if and only if this initial distribution is stationary. And so a shift endowed with this measure is what I will call a Markov shift. So in general, these Markov shifts do not need to be ergodic or mixing. One needs to impose more conditions if we want them to be mixing or whatever. Now, there is a functional analytic way of looking at these stochastic dynamical systems, which is to associate a Markov operator to each of these kernels. And now, because the kernel is a Feller kernel, it preserves continuity, so the Markov operator preserves continuity. And the Markov operator takes an observable and gives us the expected value for that observable at the next moment. So X is the current state. This K of X is the transition probability for the next moment, and this is the expected value. And this kind of operator have very nice properties. They are very well studied. I just mentioned briefly a few of these important properties of Markov operators, which probably most of you are well familiar with. But anyway, first is that these Markov operators preserve constant functions. Then Markov operator is a bounded linear operator with norm less or equal than 1. It's bounded and linear with respect to several norms, for instance, the subnorm. It's a positive operator. This is what 3 means. And the adjoint of this operator is this operator below, is the push forward on measures on the space of states. So in particular, stationary measures are fixed points of the adjoint operator. Okay, this is all very classical. I believe most of you are well familiar with this. So another interpretation for the meaning of the iterates of this cocycle is that the nth iterate by this operator of an observable phi gives us the expected value for the observable after n iterates. So conditioned to the assumption that we start with x. So, and of course, this expected value is with respect to a certain probability measure that it's actually this p of x is p of theta, where theta is the Dirac mass sitting at x. Okay, now let me introduce the main concept that will be used to establish Lagrange deviations, which is what I will call strong mixing. Maybe the name is a bit unfortunate because this is not this is the terminology that we are using, but well, you will see why we are using this terminology. So assume we have a compact metric space and a Markov operator Q acting on continuous functions. And now I want to introduce a space, Banach space of observables that correspond to some level of regularity. So in our applications, these observables are Lipschitz or Euler continuous functions. So there is a norm. The norm associated with this Banach space is always written as a sum. It's the sup norm plus a semi-norm, which is the Euler constant of the observable or the Lipschitz constant of the observable. And this is a semi-norm which vanishes along constant functions. And this is important. This semi-norm vanishes exactly on constant functions. And so we say that this operator acts in a strongly mixing way on the space of observables H. If there is a measure, then afterwards we can see that this measure must be unique. And there are constants C and sigma less than 1, such that this holds. So the meaning is the following. The meaning of this condition. So you take an observable phi, you project it on constants by taking the average, you do the difference, phi minus the average, and you get an observable here, which has zero average. The space of observables with zero average is invariant under the operator Q. This is a consequence of the operator preserving constants. And then what this property is saying is that the behavior of this operator here is contracting. Okay, so it means that the spectral radius, well, there is an eigenvalue 1 associated to the constant functions, and all the rest of the spectrum is well inside a unit circle. So the spectral radius of the restriction of the operator Q to the functions with zero average is less than 1. Okay, this strong mixing that I'm calling here, of course, it corresponds in dynamical system, it corresponds to strong forms of decay of correlation. It corresponds to the spectral gap that imply the strong forms of decay of correlation. So, and it's related with mixing, and this is the reason why we are using this word strong mixing, okay? And the way to get strong mixing in this context is to prove that the operator, the Markov operator, contracts this semi-norm. This means that the operator acts in a regularizing way. So we think of Lipschitz observables, for instance, and to have this property, you need to prove that the Markov operator contracts the Lipschitz norm in this sense. There is a kappa less than 1, such that after some certain number of iterates, the operator really contracts the Lipschitz semi-norm. Okay, now let me, okay, and the strong mixing now implies base uniform Lagrange deviations of exponential type. This is not obvious at all, but it's kind of a standard procedure, at least for people familiar with decay of correlations. From this kind of strong form of decay of correlations, one can prove this kind of theorem, like central limit theorem and Lagrange deviation principles. So there is a standard way of using Chebyshev inequality and using the spectral information that we have here to get Lagrange deviation principles and to get uniform Lagrange deviation estimates. So this is a kind of canonical route. I will not say anything about it. So strong mixing, so we've reduced continuity to Lagrange deviations, then fiber Lagrange deviations to base Lagrange deviations. And to get base Lagrange deviations, we need strong mixing. And what I claim is that this strong mixing will imply if we can get this strong mixing for this, for a Markov operator associated with this projective action of the cocycle, we are done. In the end, we get the fiber large deviations of exponential type. Okay, so now a few examples of Markov operators. The first example is the Koopman operator. If you have a map, which is a deterministic map, a continuous map, this map determines a stochastic dynamical system that to each state X associates the Dirac transition. So this is I could call it in a kind of inconsistent way. I could say that this is a deterministic stochastic dynamical system. And the Markov operator associated with this is the Koopman operator. Okay, this is, I think, pretty obvious. And now, if you look at the Koopman operator and you think that you start with a contracting map, then when we compose an observable with a contracting map, the observable gets stretched. And the stretching of the observable, of the graph of the observable, has a regularizing effect. So this kind of operator always contracts the Lipschitz or C1 norm, whatever you want. Okay, of course, these kind of dynamics are not interesting because if you just have one contraction, you will have a unique fixed point, so the invariant measure is not interesting at all. On the other hand, if you have an expanding map and you try to look at the Koopman operator, it is very bad because the effect of the operator, the Koopman operator on the graph is that it squeezes the graph. And so the regularity gets worsened. Okay, so this is why people in dynamical systems don't really use this Koopman operator to study maps that are expanding or that include some form of expansion. And the most common operator is the so-called transfer operator of an expanding map, which rules the action of the push forward action of the dynamics on absolutely continuous measures. So when we have an absolutely continuous measure, if the dynamics is smooth and expanding and we have a reference measure to talk about absolute continuity, of course, then the push forward is also absolutely continuous with respect to the reference measure. And the transfer or Perron-Frobenius operator is the operator, is this same operator, but in terms of the density functions, which is given by this expression. And then if you know the inverse branches of your expanding map, these inverse branches are contracting. And then the Perron or transfer operator is expressed in this way. So if you, and now I claim that, for instance, if M is invariant, if the reference measure happens to be invariant, then the density, constant density function 1 is invariant. And this means that you have this property. This implies that this is a Markov operator, okay? And if you forget that these depend on Y, if you assume these are constant, this is a convex combination of Koopman operators associated with contractions. So because contractions regularize, the same will be true about this transfer operator. So this transfer operator inherits this regularizing effect that is associated with contractions for the Koopman operator. Okay, this is just an example depicting what I just told you for the doubling map, so I will skip it. Let me now go to the random case, to the setting of Emil Page, and tell you what is needed to get this, to get to the strong mixing property that later leads to the uniform large deviation estimates. So you can consider a stochastic dynamical system on the projective space that to each point on the projective space associates a new point which is obtained by picking randomly a matrix according to the measure mu and pushing this point in the projective by the projective action of this matrix. So for each matrix you have a projective action on the projective, and assume for a moment something which is not true, but let me, well, I'm asking you to think that the action of this matrix is contracting. If the action, and you can think of this stochastic dynamical system as really being an iterative function system. So with maybe infinitely many functions, because the support of the measure mu can be infinite. Okay, but what you have here is the corresponding Markov operator of this action. If the action of G on the projective were always contracting, then this would be a Koopman operator, which should be regularizing. And so when we average, we are doing the convex combination, the operator would be a regularizing operator, and we would be done. We would get the kind of behavior that we want. So in general, the action cannot be contracting, because whenever you get contraction, you also need to have expansion. So this is just an example to give you a feeling of what's, I'm not going to give you rigorous proofs. I just want to convey some very general ideas. So for this hyperbolic matrix, 3 expands by a factor 3 and contracts by 1/3. The red region here, so the projective is this circle, or the circle is the double covering of the projective. The red intervals, they correspond to the region where the derivative of the projective action is expanding. So you see that the red is much smaller than the complement. Okay, so the message is that when you look at the projective action of a matrix, and the matrix is some hyperbolicity, actually it's enough that the matrix has different singular values. Then there are more points where you see contraction of the derivative than points where you see expansion of the derivative. This is a different way of looking at the same problem. So here I've identified the double covering of the projective with the interval from 0 to 2 pi. And consider this action. So this is a function on the interval 0 to pi. It's the projective action. And what you see drawn is the graph of the derivative of this function. The integral is 1 because the degree of this action is 1. This action has degree 1, so when you integrate, this must add up to 1. And you see that this function has a minimum, which corresponds to the most expanding direction, which should be here. And then it has a maximum, which is these points here. And the minimum is very flat, and the maximum is a spike. It's very, very unstable. And the stronger is the hyperbolicity, the more sharp is this behavior. So the moral is that strongly hyperbolic, actually you don't need strongly hyperbolic, you just need a big difference between the singular values of the matrix. Then you get at most time you are contracting. And then of course, for in very small portions of the projective, you will be expanding, but expandingly hugely. Okay, so this is a kind of moral. And so this shows that if you have different matrices and these spikes are out of phase, then when you average, you get a good regularizing effect. So the concept that it's needed is some kind of contraction of average, a concept that needs to be formulated, and the right formulation is the following. So here I'm talking about contraction of alpha and Euler semi-norms. So fix an alpha, and then we say that the projective action induced by a measure on the group, a compactly supported measure, is alpha contracting on average if this number is less than 1. So we have this measurement, K alpha n. Let me tell you the meaning of this measurement here. So think of the Euler semi-norm, which can be expressed in this way. So take a distance in the projective. And this is the Euler semi-norm of an observable phi. And then when you apply the operator Q n times and compute the Euler semi-norm of the heat rate, it's very easy to see that you get this inequality. Okay, this is a real simple calculation, but I will skip the calculation. Okay, it's a simple exercise. If you've never seen this, it's a very simple exercise. And then if you have contraction on average, if this measurement is less than 1, this means that the operator Q acts in a regularizing way. It regularizes the alpha Euler norm. So this means that you take any alpha Euler observable, as you iterate, its alpha Euler norm will converge to 0. And this means that the function is approximating the constant function. Okay, so if your measure has this property, then we can prove that the operator contracts the alpha Euler semi-norm, and this leads to the strong mixing that we wanted, because the semi-norm vanishes exactly at constant functions. So this property implies the strong mixing property that we need. Okay, now in general, when we have this operator, there are two conditions that are enough to imply this alpha contracting property. So one is that there is a gap between the first and second Lyapunov exponent. This gap implies that for many random products, you will have this big gap. So there will be a huge difference between the first and second Lyapunov exponent. And this will imply that you will see mostly contracting behavior on the projective. And then irreducibility concept forces these matrices to be shuffled in some sense. And these directions, they cannot be persistently consistent. And this shuffling is enough to prove that we have contraction on average for some sufficiently small alpha. Okay, this is also not so obvious, but this is a standard way. It's a standard construction. And so once you have this contraction on average, you get strong mixing. And now, as I told you before, this strong mixing leads to base large deviations for a co-cycle which takes into account the projective action. And because for a dynamics which takes into account not only the original dynamics, which, well, in this case, it's trivial dynamics because it's a shift, but the fact that this operator takes into account the projective action is what it takes to get these fiber uniform large deviations of exponential type. Okay, so this is a very rough sketch of the main ideas, the main strategy behind the proof of Émile-Lepage theorem. Then, of course, Émile-Lepage didn't use our abstract continuity theorem. There is a straightforward way that from this hyperbolicity leads to continuity. So we can prove continuity directly without using the abstract continuity theorem. Anyway, in our setting, we will really need to do this. Okay, let me now go to the proof of our theorem. So this is the context where we are. It's some hyperbolic dynamical system expressed in terms of Bernoulli shift, which lives in invariant and mixing hyperbolic measure with local product structure. This is an example of, it's a toy model if you want to, that I will use to explain the idea. So the phase space, this is the Baker map. Okay, the phase space is the unit square, and I'm splitting it into local unstable manifolds. So the local unstable manifolds are these horizontal lines. And then when we do the quotient, we get a vertical segment, and each point here represents a local unstable manifold. Okay, if you use the previous language, these local unstable manifolds will be described in terms of the past, of the negatives of the sequence of symbols, but in the past for negative integers. Okay, when you iterate a local unstable manifold, it stretches, and so it will split into several images. And then, because we have a measure mu on this square, so on x, we can disintegrate this measure along local unstable manifolds, and now we can use the disintegrated measure on this leaf to measure the proportion of points of this local unstable leaf which are mapped to this one. Of course, for the Baker map, this proportion is 1/2 in both cases. Okay, so this gives us a stochastic dynamical system. It's something which is related with the original dynamics, but now is a stochastic dynamical system. So I have a probabilistic transition, not a deterministic one. And I can think of this stochastic dynamical system in terms of an iterated function system based on two contracting maps. So F0 and F1. So F0 is the map. So if you restrict your phase space to this rectangle on the left, the action is that this is mapped to this lower rectangle. And so there is an associated contraction, which is this one coming from here to here, which I call F0. And then there is a corresponding one, which I'm calling F1. And the point is that the Koopman operator, the Markov operator associated with the previous stochastic dynamical system, in the case of Baker map, can be written like this: is Q phi is 1/2, because the transition probabilities are both 1/2 of phi composed with f naught plus phi composed with f1. Okay, so, and this operator is very well regularizing because it's a composition of Koopman. This Markov operator is a regularizing operator because it's a convex average of Koopman operators associated with contracting maps. Okay, so, and from this we could get strong mixing, and from strong mixing we could get base uniform large deviations. But okay, in the general setting, what we do the quotient, so we can identify the quotient with sequences indexed for natural negative integers. Okay, so the local unstable manifolds, they are determined by the past. This is what I was telling you. And then the probability transitions, they are defined like this. This mu x is the disintegrated measure on the local unstable manifold, and I'm measuring here the proportion of points on this local unstable manifold that move to a certain place, which is described by this new symbol I. So this is the concatenation. So x minus is the past, I is the next symbol that I write, I do the concatenation. Okay, so this map that takes x minus, and that's I in the beginning, this is a contracting map. Okay, it's a contraction. And so the operator is defined like this. It's a convex average. Actually, it's not really convex because this probability is depending on x minus, but the action here is contraction. So this is, okay, the reason why we need this assumption with dollar density is precisely to solve the problem, the technical problem that these probabilities depend on the base points. Okay, but then we can prove that this operator acts contractingly. And this is an operator that acts on observables on the space x minus, which we can think of as observables on X, which are constant along unstable manifolds. And once we have this, we can get everything else. We can get the general base large deviation. So we could prove, I don't think we could prove exactly the same that René Chazot and Sebastian Guezel did, because we are not focused on the, but the large deviation estimates of exponential type, we could get them from here. Okay, so in particular, we get strong mixing on this space of observables. Now, to finish, let me show you what we do for the joint dynamics, which includes the projective. So take a cocycle and assume now that this cocycle depends only on the past. So it's constant along unstable manifolds. Then this cocycle determines a stochastic dynamical system acting on x minus cross the projective. And this is the Markov-Feller operator that it's associated with this stochastic dynamical system. So x minus is the past. We add symbol I, it's the next symbol that we don't know, and we choose it according to this probability. And then we use the fact that the matrices depend only on the past to do the push forward of the vector V. Okay, and so this operator, or the underlying kernel, is really a stochastic way of looking at the original dynamics. And we can prove that using the fiber bunch, the pinching, and the twisting assumption, we can prove in a very parallel way with what it's done in this general Markov theory for limit theorems. We can prove that this operator is strongly mixing on this space of alpha Walder observables, and this leads to what we want, which is fiber uniform large deviations of exponential type. The only catch is that we only get this for cocycles which are constant along unstable manifolds. So this is still not the final result. We still need a final reduction, but this final reduction was available to us. This is a result that a construction that appears in this paper that I mentioned by Artur Avila and Marcel Viana. It's a paper where they prove that when we have fiber bunched older continuous cocycles, there is a way of conjugating the cocycle to one which is constant along stable or unstable local manifolds. So in the paper, they do the construction for the stable case. Here we are interested in the construction for this new construction being constant along unstable manifolds. And the point is that the actions of these two cocycles are conjugated. And here, this picture shows you, I will not explain the picture, because if you are familiar with holonomies, the picture is self-explaining. If you are not, it would take me a long time to explain this. But using this, we finish the proof. So this construction is continuous, and this construction allows us to, so we have large deviations for this observable, which is order continuous and constant along unstable manifolds. And then we can use the fact that the cocycles are conjugated to transfer large deviations. And so we get fiber uniform large deviation estimates of exponential type for the original cocycle. And so this is it. This finishes the proof. So thank you very much. Sorry, I think I'm in under the time. Or no, I'm. I think
Yeah.
a bit over.
Perfect. No, it's perfect. Yeah. Well, thank you for the talk. Are there any questions? Please activate your microphone if you want to ask. Well, sorry, I forgot to thank in a more formal way by clapping, but we are kind of remote.
No. Let's skip this. This is
yeah. So please go ahead with asking questions. I think I'm off.
No.
Well, I'd like to make a general comment that regarding the statement, the general statement is that there is this distinction between that Pedro made between qualitative continuity results regarding the exponents and quantitative ones. So qualitative simple continuity versus say Hölder continuity. We are focusing on these quantitative results, and this goes back to the work of Lepage that was mentioned, because they have applications in mathematical physics. So linear cocycles of this type are associated to certain models of physical systems called discrete Schrödinger operators. And both continuity of the Lyapunov exponents for the cocycles associated to such operators, as well as these types of statistical properties like large deviations, are directly relevant in the study of these physical models. So this is why, this is another reason other than the natural one, why Lepage first, and then and other people, including us, are focusing on Hölder or Hölder type continuity of such quantities. Okay. Are there comments and questions? Well, if there are not, first let us thank the speaker again. And I'd like to say something else. Last time, Deze suggested we end these meetings with a glass of wine or a beer or something, to turn these remote meetings into events that are a bit more social. Normally here in Brazil, after any such event of any scale, be it this scale with 90 participants or just a few, we would have something that we call confraternization, a meeting where we would socialize, which is now more difficult. So it's not my place to tell you to drink now, but at least a glass of it's well, water, yes, but at least for me, having a glass of Portuguese wine will not will actually, I think, help with my anxiety and the rage at the our leaders taking us to the slaughterhouse and all the rest that is happening. So, well, cheers. Saúde a todos. Okay. Well, I'm a good member of the community. So they suggested this. I went ahead and opened the bottle of wine before the talk, just to...
But since it's too early to start.
I know. It's after it's
no, because last time was late in the afternoon.
I know.
Unfortunately, I have only water here. Okay.
We are recording.
Yes. Okay. You can cut. You know that you can edit.
I stop the recording now. Okay.